Hello, Nix people. Today I'm going to continue my series where I talk about Eelco Dolstra's PhD thesis entitled The Purely Functional Software Model. I'm going to start off we finished part 1 of his thesis. I'm going to start off in part 2 called Foundations. And I'm going to cover the first 2 chapters in there, which are chapter 3.1 and chapter 3.2. Well, I guess it's the first 2 parts of the 3rd chapter. In the last video, we went over sections 2.4 through 2.6, talking about store derivations and deployment models and transparent source binary deployment. In part 2, Eelco gets a little more theoretical, and at least in chapter 3 here, deployment is memory management, he tries to make an analogy between files on the file system and addresses in memory. Languages like assembler programmers of assembler tend to treat memory as just one big unallocated heap. And he makes the assertion the current crop of deployment tools, RPM and apt and whatever, tend to treat files on the file system as one big unstructured heap of stuff. He suggests that maybe it would be better if we were to pull it up a layer and to impose a structure on files in the file system, much like higher level languages like C++ impose a structure on memory such that it can be garbage collected. He says that some of the underlying concepts in the stuff we discussed in the past videos might seem a bit suspicious. For instance, storing components in an essentially flat, rigid address space is very different from the way software is typically stored in most operating systems. And the hash scanning technique to identify dependencies clearly can't work in all circumstances. As we shall see, conventional deployment tools treat the system as a chaotic, unstructured component store, similar to how an assembler programmer would treat memory. Modern programming languages impose a certain discipline on memory, such as rigidly defined object layouts and prohibition against arbitrary pointer formation to enable features such as garbage collection and pointer safety. All right, so he's making the analogy between the two. We finally get to a definition of what he considers a component. We've used the word quite loosely in the preceding chapters, but now he's getting down to brass tacks about what he means about a component. Talks about the existing definitions of the existing computer sciencey definitions of component. He believes the essential aspect that should be captured by a definition of a component is deployment. And otherwise, the notion of a component doesn't add anything not already provided by normal object-oriented concepts like module, class, method, function. So he says, I will use the following definition of software component. Software component is a software artifact that's subject to automatic composition. It can require and be required by other components. And a software component is a unit of deployment. First property is, of course, entailed by the etymology of the word component, except for the stipulation that composition can be established automatically. He's making the distinction between something built to be composable rather than just source code just printed in a book. The second property, meaning a software component is a unit of deployment, implies that the purpose of the notion of a component is to be the principal object of deployment. So without being deployable, a component is not a component. Then he's referring to a paper that I had not read, but it's Szyperski about what a software component is, and he says that Szyperski says a software component is a unit composition with contractually specified interfaces and explicit context dependencies only. A software component can be deployed independently and is subject to composition by third parties. So he sort of tears this apart and says component is a unit of independent deployment. Component must be deployed in its entirety. It must have explicit dependencies only. It has contractually specified interfaces, which are subject to third-party composition. So you need to be able to describe to someone how to use it. Has no externally observable state. It's fine for the component itself to change external state, but the component should not modify itself. His definition of component differs from Szyperski's in a number of ways. It does not require explicit context dependencies. It just says that components can have dependencies. Many components have implicit dependencies, which is what makes correct deployment so difficult. Of course, to ensure correct deployment, it's necessary to make implicit dependencies explicit. And what he's actually going after here is this notion of this runtime dependency scanning step in Nix, which you don't explicitly name runtime dependencies in a Nix expression that composes a derivation. You just name its dependencies, and they can be either for build time or for runtime. You don't make any distinction between the two. He's trying to tee his way up to apologize for that. It does not require the possibility of third-party composition. As explained above, many components are not, in fact, reusable by third parties. So he's saying that it might be useful to consider something a component purely because it's convenient, because it might be convenient for disk space or network speed, to separate out things on the file system into different components. You might not want to package the docs with something, or maybe there's an optional feature that's enabled by shipping this particular component along with another one. I think that's what he's getting at here. It might be that a given component might only be useful to certain other components. It doesn't necessarily have to be useful to every person out in the world. It doesn't require contractually specified interfaces. It's enough for components to be composable automatically, but this can be as weak as a symbol table in an ELF library or the existence of a name function or Perl module. So again, he's going after this notion that we don't need to circumscribe how all dependencies are named in order to derive the runtime dependencies. He's saying we can often imply there's often enough information left over after the build to imply what the dependencies are. I think that's what he's going after. Saying the definition of component used in the thesis is quite minimal and doesn't mean to imply that a stronger notion of component is not useful or appropriate. But his thesis is about the low-level aspect of the storage of components. How do we store components so they don't interfere with each other, and such that their dependencies are known, and it's about components in the file system. He's not talking about some abstract notion of a component. For example, I think, apologies for me editorializing on here, but I think something like Smalltalk is a system unto itself that circumscribes the notion of data persistence, of the programming language, of the memory model, of the editor, of all that stuff. And he's saying that we can't do that generically. We just can't. We can't force people into all those boxes. So he's going to say the file system, that is their lowest common denominator, and that's what we're going to use to interface them together. I shall further restrict the notion of a software component to things that have an independent representation of the file system. A component consists of a set of files. Of course, components don't have to exist in discrete objects in the file system. It might be stored in a database, right? Like Smalltalk. But this is quite rare, so we won't consider it. Well, I think at this point we can presume that he is ruling out, not necessarily ruling out the usefulness of Nix as a way to distribute Smalltalk components, but he's not going to bend over backwards and introduce a bunch of language constructs and extra stuff in order to service the needs of such systems. He is going to presume that the things that we want to deploy are files on the file system. Through the file system, components require functionality from other components they can provide it. So components need to be plugged into each other. They need to be composed. Many mechanisms, Unix static libraries, ELF dynamic libraries, Java jar files, C preprocessor directives, .NET assemblies, Perl modules, Python modules, configuration files, all this stuff. All of these are mechanisms by which a composition can be realized. The one thing that they share is they are implemented as files on the file system. They can also have various binding times. Some are typically used at build times, others at run times. But what they all have in common is the composition must be established in the file system. So section 3.2, file system as memory. In this section, I recast the deployment problems identified in the introduction in terms of concepts from the domain of memory management and programming languages. That we can do this is not surprising. After all, file systems on one hand and RAM on the other hand are just two different levels of storage in the storage hierarchy. Where programs manipulate memory cells, deployment operations manipulate the file system. This analogy reveals that the safeguards against abuse of memory applied by programming languages are absent in deployment, and suggests that we can make deployment safe by trying to impose similar safeguards. Components can be accessed through paths, and we can view paths as an address, and then a string representing the path is a pointer, and accessing the file through the path is a pointer dereference. Component interference due to file overwriting can be viewed as an address collision problem. Two components occupy overlapping parts of the address space. All right, this is making sense to me. I don't know about you guys, but yeah, makes sense to me. Dangling pointers are the result of incomplete deployment. They must be prevented. In this section here, he talks about 3 ways that pointers can be obtained and dereferenced. And the first one he talks about is component A is dependent on component B. A pointer to B can be obtained and dereferenced by A at runtime. And he gives an example here of a Java class that has a constructor that takes no arguments, but at runtime it's got a run method that takes a Y object and it returns the result of the Y object's doIt method. He's saying that this is analogous to a program resolving things very, very late, like in the Unix path or the Windows search path. Program arguments, it's command line arguments to programs, and function arguments in the case of a library, like shared library or whatever, registry settings, any sort of user interaction. That is the analogy here. So any arguments passed to the constructor are analogous to build time dependencies, while arguments passed to run are analogous to runtime dependencies. In an instance of foo, there's no dangling reference. There's no possibility of a dangling reference here. Okay, so third, a pointer to B can be obtained by A at build time and dereferenced at runtime. Right, so in this case, a pointer to B is passed to and saved in the build process, constructed A, and is dereferenced during program execution. This is the notion of retained dependency described on page 23. Happens often with the Unix-style dynamically linked libraries. The build of an application stores the full path to the library and the R path of an application binary, which is used to locate the program at startup. So he gives this class example. We have another foo class here. We're going to store an instance of bar as X, and at build time, constructor time, we pass in an instance of bar as Y, and we store it on ourselves as X. And then at runtime, we return the result of local X's doIt method. So we are storing a reference. He's trying to make the analogy between a path to a shared library binary and a runtime dependency on an instance of something that is constructed at build time. And then finally, in orthogonal previous methods, a pointer to B can be obtained using pointer arithmetic. Since paths are represented as strings, any form of string manipulation such as concatenation may be used to obtain new paths. We have a pointer to user bin, then we might append the string GCC to obtain user bin GCC. The names to be appended may be obtained by dereferencing directories, that is, reading their contents. Pointer arithmetic can be used to obtain new pointers in uncontrolled ways. For correct deployment, it's essential that no dangling pointers. We need a method to prevent these. So he has a table here, summarizes the mapping concept between the domain of memory management and programming language, implementation on one hand and deployment on the other. And he's saying that in the deployment domain, disk is like memory, components are like objects, path names are like addresses, IO is like pointer dereference, string operations like pointer arithmetic. Reference to absent component is a dangling pointer, and a dependency graph is like the object graph. Kinds of dependencies, we talked about those in the 3 up above. And then he's saying that typical Unix style deployment is sort of like using language with a total absence of pointer discipline, like assembler. And he's saying that Nix is sort of this middle ground of with enough pointer discipline to support conservative garbage collection, just something that is like C or C++. Languages with full pointer discipline, like Java or Haskell, this is not a concern. He's not trying to make it fundamentally impossible to ship broken things, but he's trying to make it a lot harder. So I think that'll have to do it for this video. All right, thanks for watching.